Hello, good morning.
Good morning, Barbara.
How are you doing, Bob?
I am absolutely wonderful like I am every day.
I am glad to hear that.
I was I was watching a interview with Kevin Leary, from Shark Tank, and he calls himself Mr. Wonderful. And I just started thinking, I was like, I think I should steal that from him and call myself Mr. Wonderful from now on. So anyway.
I will do my best to use that nickname for you.
You could just refer to me as you can just call me Wonderful instead of Mr. We'll be on informal basis. So
Perfect. So, hello to all our attendees today. Welcome to another technical webinar from GMI. It is, Bob, it is really a pleasure to co-host this event with you, and I am looking forward to today's event.
me too. And it's a pleasure doing this with you.
Thank you. So I think we can start our event right now. So welcome to all our attendees. Today's topic is Intro to Intrinsic Safety, what you need to know about Zener barriers and galvanic isolator barriers. This is a very long topic, so we're just gonna go over high basic stuff on this topic. I think Bob and we can talk about this topic for days, for hours. Absolutely.
Yeah. I'm not so
Uh,
wonderful when it comes to that. I'll bore you to
uh,
tears.
yeah. But before we start with today's topic, let me go over introduction. So I am here today with Bob Johnson. Bob Johnson has many years of experience in electrical installations in hazardous locations for North America as well as international installations for ICEX. He is the owner and president of Source IEX, which is a trusted partner and distributor partner for GMI here in United States. He's also an instructor for the IECEX COPEX scheme and a inspector for hazardous area installations. So thank you, Bob, for being here today.
Yeah, thank you, Barbara.
And my name is Barbara Vasquez Isla. I am part of the GMI team here in North America, and I am looking forward for this event today. As I mentioned, we will go over GMI. Who's GMI? So GM International is an Italian company that manufactures and produces interface devices for intrinsic safety and functional safety applications. Some of these applications will be your emergency shutdowns, your fire and gas systems, burn management systems, high integrity pressure protection systems, and again, there are interface devices for PLCs and DCS on the automation industry. These sectors will be the oil and gas, petrochemical, chemical, pharmaceutical, mining, etc. GMI started in the early 90s, 1993, and has a global presence supporting customers all around the world. We have several GMI offices as well as our authorized distributors covering a lot of the country. Our production, like I mentioned, it's in Italy, and quality is one of the main focus of our production, mainly because all the products that we do are utilized on safety applications. So we test every single item before it leaves our facility in Italy. So we had 100% production tested. Because of that high quality, we are able to provide you, the customer, a 5-year warranty. And for the attendees today that work in R&D departments, we also provide a 10-year warranty availability. That means if today R&D designs a solution, they can feel confident that they will be able to produce this 10 years of today. So that's a great advantage of working with GMI products. As a global company, we follow and are certified for the most relevant standards. And you can see a list in there. ATEX ICX for North America, UL, FM, TUV for functional safety, DNV for marine applications. And this is a snip of our portfolio. As I mentioned, intrinsically safe galvanic isolator barriers, safety relays, signal conditioners, SIL3 signal conditioners, SIL3 power supplies, intrinsically safe I/O multiplexers, SIL3 HART multiplexers, SIL3 and intrinsically safe surge protectors, and our X1 series, which is a compact motherboard solution that provides intrinsic safety or SIL or both, depending on the cartridges that you utilize for your application. So a very nice portfolio out there. A quick snip of the customers that we collaborate today. You can see it's a wide range of customers, and we are glad to be able to partner with them. So before I pass the microphone to Bob, let me go over some overview of the webinar. So it will be around an hour. If you stay 75% of the time, you will receive an email with a certificate of attendees. You will also receive, everyone will receive that register, will receive a copy of this presentation, as well as a link of this recording. So the presentation is being recorded. We also want to hear from you, and I know your microphone is being muted. So please use the question and answer chat for questions or comments during the event. So Bob, all yours.
All right. All right. Well, thank you, Barbara. That's awesome. And by the way, a lot of people don't know this, but where does the name GM International come from? It's actually started off as Giorgio and Massimo, which were sons of the founder of GMI, and as a trading company many, many years ago. So that's where the GM comes from, actually. So anyway, a little bit about, and yes, and as Barbara said, we've taken some of the questions that some of you have registered, that you've posted some questions that you want us to cover. So we've tried to put some of that information in there for you to be able to look at later on. And for some reason now, all of a sudden, my Teams screen is coming up and I have no idea. But anyway, I've blocked that. So a little bit about explosive atmospheres. So just to get to the fundamentals, and this applies whether it's IS or flameproof or whatever protection concept they're using, but anywhere in which an environment in which we could have more or less oxygen, fuel, and an ignition source is considered to be potentially a hazardous location. And it could be a gas, vapor, or dust. And that's one thing that many people don't necessarily think about, but dust hazards can certainly be very explosive. So grain elevators, obviously coal mines, facilities like that, or where we're processing, even food processing, could be potentially hazardous locations. So given that the oxygen is basically always present, right, the only way to avoid our ignitions is to somehow control the ignition sources caused by electrical apparatus. And the sources of ignition will really come in the form of either heat, that could be from something that's generating a tremendous amount of heat, or it could be from an electrical arc or spark, if you will. And so when we think about intrinsic safety, that's where we're really focusing our attention on, is trying to minimize that ignition source to below the minimum ignition level of whatever potential flammable mixture is in the environment. Next. So there's more or less, there's a bunch of different protection concepts, but we pretty much kind of segregate these into more or less three different methods, if you will. There's what is segregation. So we're more or less keeping a flammable gas vapor mixture away from a potential arcing or sparking. And we can do this either by encapsulating equipment. We can do things like oil immersion. Pressurized panels is using that. So we're keeping a flammable gas outside of either a room or a cabinet. Containment is more or less a protection concept. It's been around many years, very successful. And that's flameproof, where we're basically assuming we're going to have a gas air mixture coming into contact with a flammable substance and we have to contain it. We're expecting that we're going to have an explosion take place inside of either a flame-proof or an explosion-proof box, and that has to be designed to withstand that internal explosion and continue on safely. And then finally, if you will, prevention, which we really categorize increased safety and intrinsic safety into this category. So increased safety is commonly used for junction boxes, terminal boxes, where we're limiting the heat and trying to minimize any potential spark taking place. And intrinsic safety is a concept where we're limiting the amount of energy that could be potentially be released in the form of an arc or spark within the hazardous location. So focusing our attention on intrinsic safety. And this is where you're going on, Barbara. I apologize. Yeah, go ahead and take it over.
Thank you. Yes, absolutely. So intrinsic safety, as Bob was mentioning, is going to minimize the amount of energy going into the field, right? You will not be able to create heat or energy enough to react with an explosive atmosphere. But I want to highlight a few things of what intrinsic safety protection method also provides to all the engineers out there going over installations. So one of the facts about intrinsic safety is that it's globally recognized. So if you want to standardize on a way of installation, intrinsic safety is one of those protection methods that is extremely similar. It's not the same, but extremely similar between ATEX, ICEX, and North America. So that will be an advantage. Another thing that we have to recognize is that intrinsic safety is the protection method that is allowed on Zone 0, which is the highest risk environment in our hazardous locations, as well as Class 1 Div 1. So it can go all the way into that area where you always have that exposure of explosive atmosphere. We say intrinsic safety is one of the safest protection methods. And I want to clarify, every single protection method is safe when you utilize it properly. But intrinsic safety can withstand 2 independent faults and it still be safe. So I think that's one of the reasons why it's allowed in these higher risk environments. 2 main things that for me are more critical and important about intrinsic safety is that intrinsic safety will allow you to do live maintenance when energized and in the hazardous areas. And here I want to clarify that live maintenance doesn't mean I'm going to go there and troubleshoot my field device. Live maintenance is I can disconnect that field device and replace it. So I can disconnect intrinsically safe circuits. I can open the enclosure where I have intrinsically safe circuits in the hazardous area while energized, because the system doesn't allow for that energy, that ignition source to exist. Because it's not a mechanical protection method, it also allows to use wiring methods suitable for unclassified areas. So it also provides a lot of flexibility when doing our design, our installations in the field. And the typical applications for intrinsic safety will be low energy devices, right? Because we're saying we are going to minimize or reduce that amount of energy in the field. So typical application will be transmitters. Your pressure, your level, your density, pH meter, all those transmitters, all your typical 4-20s. Also your sensors, your proximity sensors, your pilot solenoid valves, your pilot lights. So all these devices will work with a low energy. I say less than 24 volts, less than 100 milliamps. I think the standard or the rule of thumb is less than 1 watt will be intrinsically safe. So that's how you can kind of know if an intrinsic safe application could exist on that type of devices. We have put here also the standards that are relevant for when you're working with intrinsic safety. So -11 will be for manufacturers when you are designing an intrinsically safe device for ATEX, ICEX. And then you have the FMUL for North America designing of the product itself. For installation, which I think that's the majority of you guys listening to this event, when you are purchasing intrinsically safe items and you're going to install them, then you need to follow the installation standards, dash 14 and dash 25 for ATEX ICEX. And for North America, we have the NEC, the National Electric Code. 504 only talks about intrinsic safety, and the RP 12.06 about installations of intrinsic safety. So how do we achieve all these amazing things about intrinsic safety, this life maintenance, this flexibility for the wiring methods to be utilized? Well, intrinsic safety is, I think, the only protection method that is actually a system. It cannot exist by itself. So you're going to create an intrinsically safe loop. So for that, you need to have an intrinsically safe certified field device connected to an intrinsically safe barrier, or the right name is associated apparatus. And then these two will work together and it will create this intrinsically safe loop. So all that energy going into the field is being controlled, and we can ensure that even if you have a short circuit, you don't have that spark hot enough that can react with that specific atmosphere that you're installing the device. I put an asterisk in there because it's an intrinsically safe field device or an associated apparatus. An associated apparatus, a simple apparatus. A simple apparatus is a device that is so simple that doesn't really need to be certified for intrinsic safety applications, but it cannot store or generate more than 1.5 volts, 100 milliamps, and I think 25 milliwatts. An example for that would be like a thermocouple, like an RTD, a push button, just doing a short circuit device like a push button. So something very, very simple could be considered a simple apparatus. And as long as it's connected to an associated apparatus, you are creating this intrinsically safe loop. And all that, it's on the standards that we just talked about.
Yeah. And Barbara, if I may add to that, so what that means, I mean, at the end of the day, that field device, that thermocouple, that RTD, these are products that are readily available, just general purpose. You can buy a general purpose from any of your, electronics store or any of your wholesalers or what have you. They do not require third-party certification. And the one thing that has happened is that there's always questions as what actually is defined as a simple apparatus. And the latest edition of the 60079-14 that just came out gave a little bit more details as to actually what is considered to be a simple apparatus. So it's a great thing that people sometimes overlook about using intrinsic safety. And it doesn't matter if it's a Zener barrier or galvanically isolated barrier. The requirements as far as the installations are basically the same.
True. And now there are several rules that we must follow to keep the intrinsic safety, existing safe, right? To ensure that energy in the field cannot create too much energy that can react with that explosive atmosphere. So some of the rules is the first one that we just talked about is an intrinsically safe certified field device connected to an intrinsically safe barrier. Zener or galvanic isolator, it needs to be intrinsically safe barrier, right? To create that loop. There must be an energy parameter verification. That's also very, very important. And we're going to talk a little bit more about that to make sure we're actually creating that IS loop. There has to be a space and separation between intrinsic safety and non-intrinsically safe items and circuits. So IS wiring cannot touch non-IS wiring. And there are some rules. And the distance is 2 inches, I think, for North America, 5 centimeters for in the metric system.
I use 50 millimeters with 5 centimeters. Yeah, there you go.
And then IS circuits needs to be easily identifiable. And we normally think about IS with light blue which it's fine. It's a way to identify, as long as there's nothing else in your installation that has that same color. But it doesn't have to be light blue. You can also just put labels, but it needs to be easily marked to, again, inform or communicate to the people in the field that those IS circuits cannot touch non-IS circuits. Also, to take advantage of that live maintenance approach. And Bob, I'm assuming also as an inspector, it's really important for you to know if you're dealing with an IS circuit in the field.
Yeah, and actually, I literally I'm going through this right now where a customer has built some panels, and they for thermocouples, and they could not find thermocouple terminals that were light blue, and they were kind of scrambling and everything else. And I said, well, you've got gray terminals, that's fine by the standard. And as long as we indicate, we're using either blue wiring or we're using some sort of indication labels to say that these are intrinsically safe. Again, you could use like blue ductwork, you could do labeling. You don't necessarily need to have everything light blue, but that being said, that's what the standard says. But there are customers out there and end users that will say, hey, no, I don't care, I do want everything to be light blue. So that supersedes what's actually in the standards, either per the NEC or per the IEC standards. So it's always important, if I'm doing assembly work on the behalf of a client, to understand what are their installation requirements for IS, because the standard gives you some leeway, but some customers may insist on, well, that's fine, that's what the standard says, but we insist upon this. So there you go.
Yeah, and yeah, again, and you need to be able to identify which one is intrinsic safety and which one is not. So
right,
just follow your rules for identification. And lastly, very important rule for intrinsic safety is the documentation. You need to be able to, once you do the matching, you select your IS field device, you select your IS barrier, you do the entry parameter verification, just have it on file. And it needs to go into whoever has that system. To be able to confirm, the installation is done properly. And in 5, 10, 15 years, when you need to do some maintenance and updates or replacements, you can go into that document and see what's allowed and what can you do under those rules for installation.
Yeah. And I want to emphasize that that's really important to understand, because a lot of people do IS, and when they're doing it in US applications, we don't necessarily have a lot of the third-party inspector requirements that are really required in the international world. So I'll go into places and I'll do these third-party inspections, and I'll ask them for that documentation, and we typically call that a descriptive system document. And sometimes I'll get the old deer in the headlights look, like, I don't know what you're talking about, Bob. Can you kind of share with me? So, and that's what we want to look at. As an inspector is going to want to see that information. And that's basically the validation of that intrinsically safe loop.
So we talk about the entry parameters, and this is again key when we are designing our IS loop. Every intrinsically safe field device will have a set of entry parameters. This is the maximum amount of energy the field device can receive and still be safe. At the same time, every associated apparatus, Zener or galvanic isolator barrier, will also have a set of entity parameters, and this is the maximum amount of energy that it can pass into the field in normal or abnormal situations. So pretty much the rule is, if my device can handle 30 volts, I need to make sure my barrier will pass 30 volts or less, right? Because if I pass 31, I'm going to break the field device. So that's pretty much the logic here. But there, it will be this, basic math that you have just to compare for voltage, current, and power for the field device and the IS barrier. And then the cable in between is also part of the system. And for that one, you have to do the capacitance and inductance calculation, knowing the length of the cable that you're going to have. Or you can do the math, just seeing what's the maximum amount of feet or meters that you can have in that system. And this little rule is on your field device documentation. You're going to say, it needs to be paired with an IS barrier following the NG parameter concept. And you're going to give you, this information. On the IS barrier, you're going to tell you the same thing. So all this information is very easily available. We have it as a part of our poster, which I'm going to show you later on. But it's an example of an IS barrier. It happened to be a galvanic isolator barrier, where it will tell you, right, this is the associated apparatus, and these are the values of the associated apparatus, and then you need to put here the values of your device, and then you need to follow, right, the rule. And on the same document, you're going to have the information for the cable, and the same thing. It will tell you what to do. So you're just looking for this information and filling the blanks, pretty much. And that's what you need to save as your documentation for inspections. This is our hazardous area poster. It has, I think, very good information on many other things about hazardous area protection methods. But here is the IS verification example that I was showing. Yeah. Mm-hmm. Okay, we have a poll. Let me go over this one.
So yeah, as Barbara is getting that up there, you can see, so intrinsic safety kind of falls in. We talked about 3 different main protection concepts, if you will, not necessarily EX concepts, but just the general concepts. So intrinsic safety falls pretty much in one of those, if you will. So let's see if you were paying attention.
Yes. What do you guys think? What is the basic protection principle for intrinsic safety?
And don't worry, your names are not shown up, and we won't laugh at you if you get the wrong answer. So it's not a problem. We may laugh at you offline when we finish. But
no.
No, we won't do that. I always tell people there's never a stupid question. There are stupid answers, but there are never stupid questions, because when it comes to EX, a lot of people just are not aware of all this. And it's important to, and I do get stupid questions all the time, but I never feel bad about that, because I think that's always good. We want to try to make sure that we answer those questions.
Absolutely. And also will help us to make sure we communicate it better. Maybe we went too fast, or we just assumed some things. So
yeah, absolutely.
Okay, perfect. So I think many of you have responded now. So we have a little bit of, yeah.
So actually,
mm-hmm.
yeah. So it's not segregation, because segregation, we're keeping the flammable gas air mixture away from the potential ignition source. It's not containment, because that's more of a flame-proof type concept. So are we isolating it truly? You could argue, yeah, okay, we are somewhat isolating, but in reality, we're preventing a hot spark from even occurring. So that's really the correct answer. And it's a little bit difficult. It's a little bit tricky, but yeah, prevention of a potential ignition source is really what we're looking for.
Mm-hmm.
All right. So now that you know everything you need to know about intrinsic safety and DSDs and entity parameters, well, what you came here for was to find out what's the difference between Zener and galvanic isolators. And so this part of the presentation, I'll kind of go through this a little bit. So again, they're both approved. They're both widely used. I will say the original technology for intrinsic safety was the Zener barrier. That was the first generation, if you will. And it's a fairly simple device. It is a passive device. It just sits there. Think of it almost like a surge suppressor at your home or something like that. It just sits there and everything is going on. And then all of a sudden we have a lightning strike or a power surge. And then all of a sudden it kicks on. And basically these devices have on the inside, and we'll see a diagram of them, they use Zener diodes to divert any of that fault current to ground. The important thing to note here is that we divert that fault current to ground. So therefore, a requirement for Zener barriers is that we have ground. Now, in some cases, and we'll talk about some of the advantages and disadvantages, that's typically the biggest issue that we really run into with the use of Zener barriers. In many applications, we don't have a good isolated ground, if you will, and it makes it somewhat difficult to use those. And quite honestly, that was the reason why the isolated barriers were developed. And those are typically known as either galvanically isolated, or in some cases, we typically use the term galvanically isolated. We use the term associated apparatus in a lot of these standards to kind of reference, and associated apparatus is basically both of these. They both kind of fall into that. But commonly we would refer to a Zener barrier as barriers, and then isolated barriers or galvanically isolated barriers. We just call those isolators. Now, these devices operate as slightly different. They are active instruments. They need to be powered. And they use safety isolation components and primarily a transformer or optocouplers to keep that fault energy to pass from a safe to a hazardous location. So they're doing the same thing, they're just doing it in a slightly different fashion. So I think on the next slide, a little bit about the comparison of intrinsic safety versus, say, for example, EXD. And we won't spend too much time on this, but as Barbara mentioned, safety, intrinsic safety is one of those protection concepts that is in the international world approved for zone 0, where flame proof is not approved for zone 0, but it is approved for zone 1. Explosion proof is certainly one of the high protection concepts. Purging and pressurizing from a safety, it's certainly positive. There is a lot of flexibility with intrinsic safety, and there's a lot of flexibility with purging and pressurizing. Installation cost, and we've done some studies, and we've done some webinars. Actually, we did a webinar here not too terribly long ago on some of the cost differentials between the different methodologies, and I would hope you go check that out. But we looked at an installation basically going intrinsic safety for, say, transmitters versus going with the same exact transmitters, doing it either flame proof or explosion proof. And you can find that the cost of actually doing an installation can be significantly less. And certainly the maintenance cost for intrinsic safety, because we generally on intrinsic safety, once it's installed, we don't really have to screw around with it too terribly much. Where explosion proof or flame proof, we definitely have to take a little bit more of preventative care with regards to things like flanges or threaded designs or the corrosion with cast type enclosures. So just some generalities. On the next slide, right, what system, is this a poll question?
Yeah, now we have a poll in the middle of your presentation.
Oh, okay, no worries. No, this is great. I hadn't seen this one, so I'm going to guess too.
I don't know which one is. Yes, here it is. Okay, so which of the following statements about intrinsically safe loops is true? So something that we just talked 5-10 minutes ago.
Yeah.
So which one is true? So let's
Oh,
see.
I know the answer.
It's a little tricky.
Yeah, that's a good question.
A little tricky, but but let's see how our attendees are responding.
Yeah, and remember, the important thing to remember with simple apparatus, right? A simple apparatus does not require certification, right? So simple apparatus, we can just use, again, general purpose equipment, as long as it's not an energy storing device, as Barbara mentioned. So there is definitely, don't get simple apparatus confused with whether or not well, I don't want to give it away.
Okay, let's give them a couple more seconds. Anyone else wants to respond? Yeah. Okay, so we end the poll. Good job, everyone. It was kind of tricky, and I do want to spend some time on this one. So the right answer was D. Entry parameter verification is required when designing IS loops. That's always true. The first one, an EX-rated field device must be connected to an IS barrier. an EX-rated field device can be an explosion-proof field device, can be a non-arcing field device, can be an increased safety field device, right? And we
Right.
said the field device has to be intrinsically safe rated. So that's important to keep in mind, and that's one of the misunderstandings or confusions that sometimes we see in the field.
Yeah.
Well, good job, everyone. And let me.
Yeah, and that simple apparatus issue being installed in a class 1, div 1 or zone 0 area or zone 0 without additional requirements. It's somewhat true, but that doesn't mean that we can just take a simple apparatus and install it in that area. We do still have to do our validation. We have to do our, DSD or control drawing to reference that simple apparatus. So yes, I mean, we can use it installed, but the additional requirements that we would need to use or do is obviously wire that up to an intrinsically safe barrier and then validate it by the use of a DSD.
Yeah, true.
So now getting into the isolators and the Zeners. So here's the principle of a Zener barrier. So what you have a Zener protecting fuse, you have a current limiting resistor, and we have voltage limiting Zeners. And we notice that we've actually got 3 Zener diodes. So Barbara had mentioned that there is, for intrinsic safety for the highest level, IA, we actually have redundancy because it's double fault tolerant. And that's why we have multiple Zener diodes on the inside of this barrier. Because Zener diodes, if they fail, what Zener diodes will do as the voltage increases, think of it like if you're not familiar with them, they're basically, think of it like in the terms of maybe a dam on a river or something like that. As the water gets too high, then maybe the dam starts to overflow and it allows the water to overflow. So a Zener diode, as the voltage starts to increase and it gets above its rated rating, if it's 28 volts and all of a sudden we apply 29, 30, 32, those Zener diodes will start to open up. They will allow that excess energy to go to ground, and then that will cause an issue that the Zener protecting fuse will actually blow, and in the hazardous area, we will basically have a dead device. Now, the issue is with Zener barriers and barriers in general, if we do blow that fuse, generally we have to just replace the entire Zener barrier. So it's not something that we can go in and just put another fuse in them. We just dispose the whole thing and then we replace it. So that's the concept of a Zener barrier and how it works. When we look at an isolator or galvanically isolated barrier, in this case, we've introduced a safety transformer. As we mentioned, it could be an optocoupler, it could be some sort of transformer. This is actually built into the barrier itself. So therefore, this device does have to be loop powered in some way, shape, or form. We still have the Zener diodes, current limiting resistor, and the fuse. But in this case, if we have a fault condition coming down from, say, the controller, it's going to hit that transformer. And notice that we don't have to have a safety ground because we've eliminated that fault condition from actually even entering in, excuse me, into the hazardous area by the use of this transformer. So it's not a direct connection. It is using a transformer to transform the signal. Now, some people say, oh man, galvanically isolated, this is the great way to go. And Zener barriers, as I just told you, you got to have a good ground. Well, is there any application where a Zener barrier may be required where maybe this one couldn't do it? And it really boils down to, in many cases, you can use both, either. You can use a Zener, you can use a galvanic. However, there may be some instances where I do need to have that direct connection to my end device, and I cannot, for whatever particular reason, use a safety transformer. It has to be a direct connection into that field device. So in those instances, well, maybe Zener barrier is the only way that you can go. Because I've run into some applications, not too many, but a few applications where really you don't have an option. You must use a Zener barrier. But in most cases, you can use either or. The one thing I will say too is that obviously GMI is in the barrier business, If you ask GMI to produce a Zener barrier for you, they'll tell you, sorry, we can't help you, because the owner of the company basically came from the Zener side of the business and he saw the pitfalls of it. And so when he started up GMI in 1993, he said, we're only going to make galvanically isolated products. Now, galvanically isolated products are generally a little bit more expensive than the Zener barriers because they have more components. But the fact, when you start looking at it from an installed standpoint and don't need that safety ground, and some of the inherent differences between them, in many cases, it makes sense more to, if you have a choice, to go to a galvanic versus a Zener. Now, this is what could happen potentially in a Zener barrier fault condition. If we have a fault and we don't have necessarily good ground, or even if we do, we could potentially have that fault condition carry into the hazardous area. And that's a potential issue where we might have potentially create a spark that could create an explosion in a hazardous location. So if you notice in this case, we have typically on our circuits, when we do use intrinsic safety and we use Zener barriers, notice that we have to have a good ground that typically is separate from our normal, what we would call normal dirty earth. We might call it clean earth, we might call it IS earth. Many people will call it different things, but we want to keep that separate from our normal dirty earth. And there's some things that you have to do with regards to addressing that. But generally speaking, we want less than 1 ohm resistance between the Zener barrier, in this case, to our ground. And we want to keep that clean so we don't have any noise, feedback, fault conditions, or anything else kind of coming up through the barrier on the backside. And again, the same thing in the isolated barrier under a fault condition. What happens again, just like we saw in that previous slide, we're using that safety transformer so we don't have that direct connection. Typically under a fault condition, we don't have these problems that we would have with a Zener barrier. Now, how do we ground Zener barriers? And typically, in many cases, you'll notice that we actually have 2 different ground connections. This is not a requirement by the standards, by the way. This is more or less what typically is done in industry. They'll have actually a safety ground, and then they'll have a redundant safety ground. And the reason why that's done is that you're actually, at times throughout the life of the installation, you'd actually go back in and you're supposed to go and check and see how the reliability is of this ground. Well, if this is in service and we want to disconnect any ground, well, then all of a sudden we disconnect it. We've taken the protection concept potentially offline. So a lot of times they'll actually have 2 connection points for our IS barriers after it's left its barrier. And that's strictly just to be able to test the quality of the ground as time goes on. So that's why you see that. Maybe sometimes you might even see a specification being called out for that. That's generally the reason why. And again, this is a fault condition where we could be tying into the structural ground and where that potential could take place. So that's what we don't want to have. Now, talking about intrinsic safety a little bit from an inspection standpoint. So this chart is from the 60079-17. This is actually an older version, but it hasn't changed from the latest version of the -17 with regards to intrinsic safety. But when we do an inspection of intrinsic safe installations, these are some of the key things that we really want to check, right? And so if you're wondering, hey, an inspector is going to come in and look at my skid package that I'm building, or coming into my facility and do a final EX inspection before everything is done, these are the checks that we want to actually go through. And I just highlighted a couple things here. So we see that earth continuity is satisfactory, connections are tight, earth connections maintain the integrity of the type of protection, intrinsically safe earthing is satisfactory, insulation resistance is satisfactory. So these are the types of things that I want to make you aware of, because in many cases as designers, we're not necessarily involved at the final commissioning. And so it's important to understand that these are the things that, we may do a design of a project and everything else, and then all of a sudden, again, inspectors like me come in and say, hey, where's your DSD? And you're like, wait a minute, I don't know what that's all about. Well, okay, make sure you do your DSD, regardless if it's Zener or galvanic. but these are also the things that you want to be aware of. So when you're doing your design, right, these points are basically spelled out in the installation standards anyway, but it's really highlighted in these inspection requirements. So I always tell people, I say, look, even if you're not going to do inspections, understand the relevant inspection standards so you can check your equipment before a third party comes in and you're aware of all the things that that person is going to be doing, because it's always better to have that information, know it ahead of time, and you can fix it or confirm it before somebody like me shows up in your facility and starts going on and say, hey, have you done this? Have you done this? Okay, well, let's do all this. And then we find out, okay, no, we got problems here. We're going to have to fix it. So I tell designers, engineers, even if you're not doing installations, even if you're not doing the inspections, pay attention to that information, because again, that's usually the stuff that happens right before material is shipped out of your facility and getting ready to go to a customer. And that's where you don't want surprises, right? Because then all of a sudden it delays everything and adds cost and everything else. So again, just to kind of summarize here, some of the advantages and disadvantages. Again, the galvanic, no safety ground requirement, better overall accuracy. There is a lower installation cost. It can use, again, grounded or poorly isolated sensors. In that case, again, the Zener diode, we have that dedicated safety ground. We do have those routine checks. The field sensor must be isolated. There is an issue with Zener leakage. So Zeners over time can actually change. And so that can affect the accuracy of these Zener diodes. That's not terribly uncommon. It's not a common problem, but it does happen over time. And that's another reason why we have redundant Zener barriers on the inside of these products.
We have one more poll.
I think you guys will get this one.
Mm.
Everybody, we're all going to get 100% on this one.
Okay, so let's see our attendees. Is a dedicated and low resistance ground required in a galvanically isolated barrier installation? So let's give them a little bit more time.
It reminds me of some of the exam questions that we give in some of the courses that we run. Sometimes I always tell people, it's like, well, if you don't know, pick the longest answer. I wouldn't say that that's correct in this case, but actually, ironically enough, I did this one time with one of the courses that we run on the exams, and you found that the longest answer in many cases was actually correct about 50% of the time. So, just for test taking in the future, no matter what exams you're taking, if you find the longest answer, it very well may be that. And I will tell you this is another thing on taking exams. If you see two answers that are almost identical, but there's a word that's changed, it's almost always going to be one of those two. So there you go. Always, always, always.
Good. Okay. So you want to explain this question, Bob?
Sure. Yeah, absolutely. So the answer it's not required, right? Because a low resistant ground for galvanically isolated is not required. It is a required for Zener. So it's a little bit of a tricky question. And then, of course, if it is required, it must be less than 1 ohm resistance, which is true, but that doesn't apply to galvanically isolated. And then again, it depends on the field device isolation characteristics. Well, that's a long answer that I don't really know exactly what it means, but yeah, I guess you could say that that could be it. But the correct answer, it is not required.
Perfect. So at this point, we finish with our presentation, but we're not finished with the webinar, right, Bob?
Yeah, no, we're not done. We're not letting you go yet. Well, you can always log off and say goodbye. But we do have a couple questions that we'll go through and hopefully answer for you. And certainly if you have some additional questions while we have another 10 minutes or so to finish up, if you do have some questions, I think Barbara, you have a chat function there that you might be able to, I don't think I can read it right now, but if there is a chat that you have, If you do have a question, please feel free to ask and we'll try to answer them online. Or if there is a question that we don't get an opportunity to finish here, please feel free to reach out to either Barbara or myself, and we'll definitely try to answer any questions that you guys might have afterwards.
So when you guys register to this webinar, there was a section to if you wanted to ask us something ahead of time. So we appreciate everyone using that tool. We have handpicked a few of those questions. So one of the first one was, what are the factors most commonly misunderstood about Zeners and isolators? And we answered it with some of the things that Bob and I have seen in the field, that we have seen in our experience. So I will say the first one is, if it's working, it must be safe, right? And I think that's one of the challenges with the Zeners, that if you ground it or you don't ground it, it still works.
Yeah.
So, or if your ground is 10 ohms, it still works, right?
Still works. Yeah.
So that's one of the misconceptions. Not checking NT parameters. There's a lot of customers that says, I have my IS field device and I have a barrier. Boom, done. I have IS protection.
Yeah. One thing, let me add to that, Barbara, too, also. I mean, just as an FYI, if you have a field device that's not working, then, obviously troubleshooting that circuit, that loop, it could be, obviously there may be a problem with the card or something like that, or the signal from the PLC or DCS or whatever it is. And then, of course, in many cases, it's not that, it's actually down to the barrier itself. And most likely it's probably a blown fuse. So one of the things that is pretty common, and you just want to make sure that if you're responsible for any maintenance people on intrinsic safety, is that what I have seen multiple times in existing installations, where a jumper will be placed between the input and the output on an intrinsically safe barrier. Now realize at that point, you've basically defeated the barrier. Now your device will work, and as long as we don't have a fault, it's safe. But the moment we have a fault, then we have no protection. So just be aware of that. Emphasize that for any of your maintenance operations people, that if we do have a barrier that is not working and it's not a signal coming out from the panel, then it's probably a blown fuse. And that's what you would, you can check to see if it's a blown fuse. But if it is, don't just have them jumper it, have them replace it.
True. Another question was, are diodes still used in diodes are still used for intrinsic safety applications? And I think, as Bob showed on the Zeners as well as the isolator barriers, they both utilize Zener diodes in their construction.
Yeah. And along those lines too, Barbara, I mean, sometimes people will build intrinsic safety into maybe their boards down at the board level. So, I mean, you could buy a PLC or you could buy something else that actually has intrinsic safety built in. And they probably have Zener diodes built in on the board level, as opposed to using a separate, intrinsically safe barrier from GMI or any number of manufacturers. So, yes, they will typically still use the Zener diodes. In some cases, they'll also do a galvanic, where they, but that's not uncommon. And it's very common on the inside of boards that will be intrinsic. The output will be intrinsically safe, that they probably have Zener diodes on the board, and then they'll have a dedicated IS earth out of that panel.
Another question we got: how to complete the necessary grounding when using Zener barriers? And I think Bob already covered that. So one of the main things, right, is less than 1 ohm resistance on your clean ground. And both the standards for United States and Canada, or whoever follows the NEC installation rules, this standard will cover the requirements for the grounding, and the gauge of the cable is important. And for international, I saw, you, like Bob was saying, you could use 2 ground pads or 1, and there are also some rules about the gauge of that conductor to be utilized.
Absolutely, yeah.
Is there a reason I should use one over the other? Yeah. So I found on the standard there is this one sentence: associated apparatus will galvanic isolator between the intrinsically safe and non-intrinsically safe circuits is preferred. However, what Bob was mentioning, both are associated apparatus, both are allowed per the standard to be utilized, both will give you the intrinsic safety protection in the field. It really depends on your application and some of the challenges that you might have on that specific area where you're installing the system.
Yeah. One thing I want to add too, and I know this is not a sales pitch presentation, but one of the big downsides, and I don't think we had this in our slides, but was traditional galvanically isolated barriers from manufacturers, including GMI, were fairly thick. They were about 20 to 25 mils wide because we have a transformer on the inside. We have a lot more devices on the inside of the package. Where a Zener barrier, they typically were much thinner. They were usually about 12 to 15 millimeters. So, you know, one of the big advantages on Zener barriers was the amount of density when we're putting them inside of a panel. One thing that GMI did do with their latest generation of barriers, they shrunk down the size, the width of their galvanically isolated barriers, but they stand up a little taller than maybe some of their competitors' product. But you're able to get kind of that same amount of density, if you will, using a galvanic versus a Zener. And that's, I've run into some applications where that was actually a very, very important point. The other thing too to remember, and this is true either for galvanic or isolator, but it's more common for galvanic, is that you will find them being multi-channels. You know, you can use, actually, they have certain barriers that are actually able to run either 2 or even 4 channels with a single barrier. So you might even have 4 devices going through a single barrier. So those are some things that, you know, if you think about when you're doing your design work, you can actually do some things that maybe even save cost even more.
And I will add, Bobby touched a very interesting point there, as well as having that multi-channel option. Usually galvanic isolator barriers have also signal conditioning on it, right? So you are
Yeah.
able to get, let's say, a thermocouple to a 4-to-20 conversion on it. So that one device, you do these 2 requirements, right? So
Yeah.
conversion, or it has built-in dry contact for alarms, or it can do some multiplexer, requirements on it. So sometimes, not sometimes, galvanic isolator barrier will have some signal conditioning that you could take advantage of it if your design allows it.
Yeah. Yeah. No, that's a good point.
Mhm. Can I install an IS barrier in the hazardous location, or do they have to be in the non-EX area?
Yeah, that's a great question. It comes up an awful lot. So if you notice on the labeling on this particular barrier from GMI, that first line string that's up there where Barbara's got her little mouse over there, you'll notice that that's the Roman numeral 2, 3, 1 parenthesis, and then the EXEC, and then in brackets you see an IAGA. What that's telling us is that that barrier is suitable for installation in a zone 2. The GC is telling us that that's per the EPL, per the IEC, as well as ATEX now markings. So the barrier itself, in this case, can be installed in a zone 2 environment with the output in the brackets that you see there, IA. It's saying, in effect, the output for this barrier, can actually go into a zone 0. So that's what that marking string is basically telling us there. Now, the good thing is, if you're familiar more on the North American side of things, if you look down below, you'll see at the very right next to that little UL listed bug, it'll say actually Class 1 Division 2 groups A, B, C, D, Class 1 Zone 2, so forth and so on. And then it'll actually say for use in a Class 1 Div 1 for circuits for use on a Class 1 Div 1 area. So what that's basically telling us, in effect, we can install barriers depending on the brand, depending on the model. Most barriers are like this from most brands. They will allow you to install them in a Division 2 or Zone 2 area. If, on the other hand, we already need to install, or we need to install this into a Div 1 or Zone 1, well, I'm not sure if you'd have to install it in Div 1 because anyway, Zone 1, but we need to go protection into a Zone 0. then we can always place barriers on the inside of panels that maybe are pressurized or EXD flame proof. So that's certainly an option as well.
Perfect. So with that, we got to the end of our questions. We do have a question on the chat that I think we might need to address later on. So let me, we do have several live webinars scheduled on the website. So if you want to see what else is coming up, feel free to go to the website and see the other webinars, live webinars we'll be hosting. All the webinars are being recorded, so you can find them on the GMI channel, and you can see some of the other presentations Bob has hosted as well on similar topics.
Yeah, if you got tired from listening to me today and you just want more, I'm there. So.
And let me move this. And we appreciate everyone for your time. We have the question in the chat. I do want to respond to this question, but I do need your email address to address it. So I don't know if you can share with us. It's about the capacitance on the cable. We'll have to review this a little bit more detail to provide a proper answer.
Yeah.
So if you can,
Yeah, and again, we're gonna obviously end the webinar here shortly, but if there is any other further questions, please don't hesitate, reach out to myself or Barbara or both of us, and we'll be happy to try to answer those questions offline and send you the information and all that good stuff. So if you do run into some technical questions, or if you even have application questions, please let us know. We'd be happy to help. One thing I do want to add just at the very end too, for any of you, Barbara had mentioned a lot about functional safety, that a lot of the GMI products have functional safety SIL ratings. If any of you are located here in the United States and would be interested, GMI is hosting a functional safety training course, a TUV Rhineland functional safety course, I believe in September. And the gentleman who's doing it is a gentleman by the name of Tino. And it's going to be here in our facility here in spring. And if you at all are interested in functional safety, Tino is by far and away, I've known him for forever. He is the best instructor on functional safety of anybody in the world. And I mean that with all sincerity. And if you are interested in finding out more about functional safety and going through I think it's a 5-day course, and it's a great course if you want to learn more about functional safety. And Tino is absolutely outstanding.
Absolutely. So if you want more information on that training or any other training, feel free to reach out to Bob or myself. If you want to, if you have a topic that you will want us to cover as well, feel free to send us an email, put it on the question and answer chat, or fill out the form on the website. We look forward to continue doing these events for all of you guys. And Bob, thank you so much for hosting this event with me. I really enjoy it. And I look forward to the next one.
Yeah, me too, Barbara. Thank you so much. And thank you, everybody.